Look what I'm doing over here. Somebody's got to explain this to me. Overflowing water. Yes, that's very good. Why is the water overflowing? Because you put too much in. All right, take a look. You watching? Pay attention now. Here's my jar. You just saw me fill with water. And a homeroom attendance slip. Watch. Oh, Emily's late. Perfect. Emily, stay here. Stay right there. Emily is in the splash zone. So, she may get wet. You watching? Come here, Emily. Come here. Come here. Come on. You wanted to be on TV, huh?
Yeah.
All right. Well, you're going to be on TV. Come here. Ready? Ready? No, don't touch it. What are you, crazy? Are you joking?
This is a joke. This is a joke.
I didn't get fired. Very nice. Don't pull that out. What's going on here? You can sit down now. Late person. Go. Don't. Go get it. All right, look at it. What is going on here? What's holding that water up here? Why isn't it coming out? You can sit down, Carol Merrill. What?
Pressure.
Pressure? Pressure. Really? Is it?
Sure.
Let's see. Hold on. What? Wait.
You're spilling some.
Oh, no. Wait.
Oh, God.
There you go. Negative. He's right. It is pressure. The other classes saying stuff like gravity, density, adhesion, cohesion, surface tension. Look at this. It's pretty impressive. That's pretty impressive. All right, that was pretty heavy, too. That was pressure. Now, I hate this song. Actually, I really hate it. It's not that bad of a song. But because it has in it exactly what you will say for your answer. What is pressure? Pressure is the force pushing down on something. Now, I just did that demo for a couple of reasons. One, it's pretty impressive. 2, there was a chance of getting Emily soaking wet. 3, that it's proving it's not pushing down on anything. The pressure, all right, that was keeping this water up here was pushing up. So what are you talking about? Because most of you, when I say the word pressure, maybe Marvin's wasn't thinking, but a lot of you probably were. You're thinking it was the water pressure, or it was suction, or something like that. No. It's the pressure in this room of the air molecules hitting this thing and hitting that paper that was under my hand, or right here. Oh, it wasn't under my hand the whole time. This paper that was like this, the air molecules banging into this was enough to keep all of that water. They say, well, there's no way there's that much air pressure in this room because this is awful heavy. But actually, there's way more than that much air pressure in this room. Okay, let me show you how much air pressure is in this room. Check this out. This is a steel bar, 1 inch square. See it? And it's about, I don't know, maybe about a meter high, a little bit more than that. This is how much weight on every square inch of your body right now. So, well, no, that's a lie. There can't be that much because I don't feel it. Why don't you feel all this pressure? No, not gravity. And no, not because you're used to it. Why?
Because of the way the human body's built.
Well, be more specific. What is it about the inside of your body?
Pressure.
Yeah, the pressure inside your body is about the same as the pressure in the room. About the same. It's not much different, so you don't feel anything for that reason. You do notice the difference if you change the pressure of one or the other, especially if you change the pressure in the air. If I drive up a tall mountain, steep mountain, what happens to my ears? They pop. Why do they pop? Because the pressure inside behind your eardrum is greater than the pressure as you're going up the mountain. So they have to be released. And that's one of the problems with babies on an airplane. Why do babies cry on airplanes so much? Because you're taking off and landing and changing pressures. Especially on landing and takeoff, babies will cry because their eustachian tubes aren't well developed. Maybe some of you guys, when you were kids, had tubes in your ears. How many of you had tubes in your ears? Probably quite a few. Usually about a quarter of the class says yes. And basically, they can't equalize the pressure. Babies can't, so they cry. They get it hurts. It hurts when they're going up and down. Same thing's true if you go underwater. You can feel the pressure on your ears, right? On the deep end of the pool, you can feel that pressure. Because right now, the pressure, well, it's a little bit greater. If I cut myself, I bleed. If I cut a vein or an artery, I mean, it's going to really shoot out. So the pressure inside, I don't want to do these things. I could show it to you, but the pressure inside is a little bit higher than the pressure outside the room, but it's very, very close. Where is there a place in your body where the pressure is less most of the time in your body when you're, well, at least half the time in your body than the air?
The lungs.
Where's the place in your body? Your lungs, yeah. I didn't hear. Did you say lungs? I didn't hear Jacob say lungs, Jared. I didn't hear you say lungs, but yeah, absolutely. Because the reason you're able to inhale is by making the pressure inside your lungs less, and that sucks air in. Okay. All right. Well, we'll talk about all these guys. This is all about pressure today, and also a little bit about temperature. We have to talk about this because gases absolutely are dependent on what the pressure is. Okay. Take a look. I said this yesterday, and I'll repeat it again today. It means nothing for me to tell you I've got 100, in this case, I got 95 milliliters of a gas. Means nothing to me, unless you tell me the pressure in the room. Because look what happens. A little bit of pressure change, big change in the volume. Pull back on it, big change in the volume. Telling me how many milliliters I have of this gas means nothing, because the pressure will change the amount you have. All right, now before I get actually to the definition, well, actually, I have you write a definition. I want to go back to something after this. It's a force caused by the collision of particles with the surface of the container. Write that down, because that's a good definition. And let me explain it to you, even though I've just explained it kind of with two different little demos. I want to go back to that animation I showed you yesterday. Now read that whole thing, because I'm taking this away. And you need to be able to not copy one word at a time. It's the force caused by the collision of particles with the surface of the container. Let me show you again with this. Turn the light off again, Marvin. Put some gas in here. And let me show you what's causing pressure in this case, okay? What's causing the pressure, and what actually was enough to hold this guy upside down, hold the water from coming out, is simply the molecules, these guys, banging into these containers, into the sides of the container. Notice they're banging into the top, the side, the bottom. So the last thing I want to hear as a definition for pressure is it's the force pushing down on something, like the song says. It's not. It's the force pushing in all directions. Now let's look what happens to that pressure. Here's a measurement of the pressure. When I heat this guy up, if I make those guys move faster, what happens? Well, the pressure is rising. Those guys are moving faster. I'm giving them more energy. The temperature is also rising. Notice that too? Okay? We're going to talk about temperature today as well. They're moving faster, so they're banging into the sides of the containers more, and therefore greater pressure. Okay? Makes sense. So that's what I'll come back and show you. I told you I'm going to show you this a couple of different days throughout this chapter. All right, back to pressure. All right. Now, as I just showed you, light back on? As I just showed you, it acts in all directions at once. Pressure does. It doesn't seem possible. We don't feel it that it'll be enough to hold all that water up here. But the fact is it can hold way more than that. The pressure in this room, as I showed you with that steel bar, is way stronger than you think. Let me show you another way we use pressure, and we measure pressure, actually, the one way we measure pressure. I'm going to make it right here. Take a look at this. Okay? Beaker full of water and a very big test tube. It's actually called a eudiometer, and we're going to use it to collect gases. All right, we're going to use this to collect gases because it has markings on it. We tell how many milliliters of each gas we have when we collect them. Now I'm going to add some water to this. You watching? Add some water to this guy. Doesn't matter how much I add. I could fill it all the way up, and it still would work. And I'm going to turn them upside down in the water. Now watch. When I do that, you may notice that the water doesn't come out. And it's not that I'm sticking on the bottom. I could hold this anywhere and the water doesn't come out. It stays up here. Okay? And like I said, I could have poured all this in. I just did it because the camera could pick it up from here. I could have filled this all the way up. Matter of fact, I could have filled it up with a glass tube as tall as the ceiling, pretty much. Now, there is a limit beyond which I can't fill it and have it stay. But I certainly could fill it this high. What do you think would happen if I took this whole thing up to the top of a mountain? Where would that water be? What's keeping that water up here? The air molecules banging into the surface of this water is able to push and hold all that water up there. If I go to the top of a mountain, is there as much pressure? So what would happen to the water level here? It would drop, right? It would go down. What if I were to take this down to Death Valley, where maybe there's more pressure? All right, it's going to rise. Okay, so and by the way, this is a great way to tell weather. If I find that this is falling over a period of a few hours, that means there's a low pressure front coming. Probably what's coming? Maybe a storm. If I find that this pressure is rising, it means there's a high pressure front coming. And that means probably going to have clear weather. And that's why Tom Clark quotes this almost every day. What is it? What have I made? A barometer. Exactly. This is a barometer, right? And that's what a barometer is. Now, you might be saying to yourself, but doesn't he tell you in mercury, tells you what the mercury is falling or the mercury is rising, if you ever listen to him? You're right. We do not make barometers out of water. We make them out of mercury. Here's why. The size of this tube would have to be about as high as the ceiling in order to be a legitimate barometer. And I don't want to have to get up on a ladder. Tom Clark doesn't want to have to get up on a ladder and read where the volume or the value is, with how high it is. So you use mercury. Why mercury? Because it's more dense. And so the size of a mercury column, let me explain to you. This is about how high. You're looking here, Emily? Look here. This is about how high the mercury is on a given clear day, clear sunny day. Right about there. From here to there. Okay? About that much. 760 millimeters high. Okay? Right about there. From my two hands. And, of course, like I said, if this was water's less dense, it would have to be about as tall as the ceiling, much higher. All right? So that is called a barometer. By the way, this is illustrating something else for me, too. What happened to my water? Inside of here, it was clear. It's green now. What's that property? Diffusion, exactly. All right, so barometers measure atmospheric pressure. I just showed you what a barometer is. A barometer is just a pool of mercury with a tube of mercury filled up. And depending on how high that tube is, that mercury is, I should say, in that tube, able to support, we could tell the pressure in the room. We could tell the pressure of the atmosphere. We use it for weather. We use it to determine whether it's going to be raining or going to be clear based on the barometric pressure. Anybody have a barometer in our house? Nobody? All right, because a lot of people have like decorative ones. They look like for like a ship, a sailing ship would have like brass ones and stuff like that. Nobody has one. Most of those are not based on mercury. They have a different way to do it. Okay. Now, the way I would measure the pressure in the room is a barometer. The way I would measure the pressure of an individual gas is something like this. Take a look at this thing. A lot of demos today to get through here. Check this out. This is like a big U-shaped tube. All right, down at the bottom, it's filled with green water again. All right, and it's pretty tall because it has to be because once again it's using water instead of mercury. I've got a gas in a syringe hooked up to it, and right now these two are at basically the same level. These two water levels. If I increase the pressure of this gas, if I push in on this syringe, watch what happens to these. See, it goes up. And there's a difference between it. The difference between these two levels, had this been mercury and not water, again, why don't I use mercury? It's poisonous, right? I'm not going to have mercury. They don't even allow us to have mercury. If I had this filled with mercury, the difference between those would be the pressure I was putting on that gas. If I pull back, all right, I could decrease the pressure. And this is how what's called a manometer works. So watch again. There it is at the same level. If I push down on it, all right, or if I pull back on it. And the difference between those two levels is the pressure of that gas. That thing is called a manometer. And you may have seen something similar to that in the doctor's office. I'm sorry, I forgot to give you the definition of a barometer. Sorry. Write that down first before I get to manometer. By the way, I should, before I come back to manometer, talk a little bit about, this explains the units of pressure a little bit. People, you guys are going to have to get used to a strange unit for pressure. Doesn't seem to make sense. But now you understand it because you've seen the barometer and the manometer. Pressure is measured in millimeters of mercury. Okay? It's measured by how high the mercury level is, or the difference between two mercury levels. So it's strange. I mean, the units of mass are what? What do we measure mass in? Grams. What do we measure volume in? Liters. We measure length in meters. Now the strange part about this guy is we actually measure pressure in millimeters of mercury. How high the mercury level is. How high it can be supported on a given day. Okay? That's the actual definition of that's the actual unit we're using. How high the mercury is. All right? Now, back to my manometer, which I showed you a second ago. I got ahead of myself. The manometer measures the pressure of an individual gas. Same basic concept. All right, it's a difference in the mercury levels in that U-shaped tube that I just showed you. By the way, I said you may have seen one in the doctor's office. What would you be having done if you saw a manometer of some type in a doctor's office? What might you be having taken?
Your blood pressure.
Blood pressure, sure. Anybody know the name of that piece of equipment? Nobody? It's called a sphygmomanometer. Sphygmomanometer, I know. But the last part of that word is manometer. And all it is, if you've looked, I think almost all of them now are digital readouts, and you don't get to see it. But I remember just recently over at Allie's, basically you can watch that column of mercury rise when she's pumping up the blood pressure cuff, and then you could see it fall. All right, back down. Did anybody ever see those kind? Or are they all digital now, pretty much? I guess. Yeah. Anybody know what that's measuring? What's that measuring? How is it measuring your blood pressure? Anybody know what you're doing there?
It's your arm expands until it stops, and then it just reads how.
Yeah, that's right. When they put that cuff on, they cut off the blood flow. They have that cuff expand, they cut it off, and then they let it go slowly to see where, and they'll be listening for where the blood is actually able to get back through. And then they can tell at what pressure that happens. And what's a normal blood pressure? There's two numbers. Remember two numbers? Anybody know them? 120 over 80. Ever hear that? 120 over 80. What do they correspond to? There's two different things your heart does, right? You have the ventricles. Remember this? And the atrium. So when the ventricles contract and when the atria contract, it's the pressure of the blood. All right, based on that. It's basically 120 over 80 is about normal. All right, good enough. So there you go. That's all I have to say about pressure. I got to show you now how to do conversions and calculations with pressure. All right, so like I said, the units of pressure are going to be measured in millimeters of mercury. However, as with most cases, we need something besides that. And we do have other units we're going to use. There's actually about 4. I'm only going to give you 3. All right. First one's called atmospheres. Atmospheres are useful because it's about the pressure in this room right now. 1 atmosphere is. Okay? So it's nice because the millimeters of mercury are pretty large numbers. Like 760 is about normal pressure like in the room. Whereas atmospheres would be 1. So it's just a smaller number, just different units. Torr is another name for a millimeter of mercury. So here's how they're related. You ready? 1 atmosphere contains 760 millimeters of mercury, or 760 torr, same thing, which is what we call standard pressure, which we'll be using in calculations throughout the chapter. And the next chapter as well. We're going to be doing 2 chapters on gases, remember. You're going to have to know standard pressure is 760 for both of those chapters throughout. Okay? Now, before I get to the 2 examples I'm going to do, how hard are these examples going to be? What am I going to do? They're going to be conversions. I'm going to ask you to convert atmospheres to millimeters of mercury or torr, or vice versa. Now, by the way, this is MMH. I don't want to hear anybody when I call and you say MMHT or mummahugs. What does that stand for? Millimeters of mercury. HG is a symbol for mercury. Torr is just a shortened way to say the same thing. And these are not places you would draw cash from. They are atmospheres, not ATMs. All right, let's do 2 conversions. One quick one here. Convert 1.4 atmospheres to torr. Remember I said yesterday you're not going to need a heck of a lot of information from the previous chapters. One of the few things you almost always need are the simple ability to do conversions. What will I write down first to do this conversion? Yeah, 1.4 atmospheres. And then I would have what units on the bottom? Atmospheres. On the top, torr. And then I fill it in. Now look back at my, just a second ago, told you the way they're related. How are they related? 1 atmosphere contains 760 torr. Do the math. What do you get? Come on, somebody's got to do it quick.
1,064.
All right, so if it's 1,064, don't write that down. It can only have 2 significant figures. What would he be?
1,100.
Right. 1,100. Got it? 1,100. All right, let's do one more. Doing it in a different direction. Try this guy, converting 455 millimeters of mercury to atmospheres. Okay, we again know what we're going to do. We're going to take 455 millimeters of mercury and write that down first. But this time, what units are going to go on the bottom, Nikki? Good. Millimeters of mercury. And on the top, what's going to go up there? About
ATM.
atmospheres. Don't make a withdrawal from the atmosphere. And then 760 millimeters of mercury. Do the math. What do you get for that? 0.599 atmospheres. Now, before I have one more thing to do here for temperature in a second too. For notes, I'm doing a lot. Trying to get all this in a shortened period. Let me say something before I forget. These numbers will not limit you significant figure-wise. Neither the one, and we're used to that, right? Whenever we did conversions, 1 mole on the bottom, 1 didn't mean I had to have 1 significant figure. But this guy doesn't either. He doesn't because he's our standard. And we're saying 1 atmosphere equals exactly 760 torr. So it has an infinite number of significant figures. So you're only going to be limited by these guys that you're using over here when doing these kind of conversions from atmosphere to torr. Okay? All right. Now let's talk very quickly, because this will not take me anywhere near as much time. You know about temperature anyway. We've already talked about what temperature is, the measure of the kinetic energy of the particles. We talked about that way back in the first chapter. We talked about how the difference between heat and temperature. And temperature measures the intensity of the heat. You had that same question on your midterm. Okay? If I increase the temperature, I make the particles move faster. I'm giving them more energy. And therefore, if I put this same syringe into ice water, it's going to shrink. And if I put them into hot water, it's going to expand. If I make that gas hotter or colder, the particles are going to move faster or slower, and therefore their volume is going to change. So, but here's the difference, guys. And you're going to see why this makes... I'm not going to have time to talk to you about it today, but we need a different scale. Normally, we've used Celsius. And I know you're all saying, but we use Fahrenheit. We're never using Fahrenheit, period. Okay, normally we use Celsius. Does anybody know what we have to use to talk about gases? Kelvin. Kelvin, exactly. We're going to have to learn how to convert into Kelvin if you don't already know. My guess is you probably do from bio. Integrated, you had a little bit of that, didn't you? Do you remember Kelvin a little bit? Some of your class knew about it too, so I'm assuming you got it somewhere. I just don't know where. Maybe you got it in physics. What's that? Yeah, not Kelvin cycle. That's Calvin. That's biology. No, the Kelvin, maybe it was in physics. I don't know. But either way, I'm going to show you right now how to convert. It's very simple. Standard temperature is 273 degrees Kelvin, or 0 Celsius. 0 Celsius is 273 Kelvin. They're the same thing. And the value of 1 degree in Celsius is the same as the value of 1 degree in Kelvin. So all I have to do my conversion is this. It's a little easier, actually, than the other conversions. Kelvin is the Celsius plus 273.
The junior class meeting that was scheduled for today at 2:15 has been canceled and will be rescheduled for tomorrow at 2:15. Thank you.
So Kelvin simply equals whatever the Celsius value you have plus 273. That's all you have to do. So very quickly, I'll do 2 examples, and then I'm done, and the bell will be ringing right when I'm done, just about. Convert 400 Kelvin to Celsius. What are you going to do? Well, it's not quite set up the right way, right? I mean, if I leave this equation as is, all right, I kind of have to rearrange it, don't I? All right, because I'll have, 400 Kelvin equals degrees Celsius plus 273. But can I rearrange it? Can you rearrange that equation? I would certainly hope so. What are you going to do to both sides? Subtract 273. So degrees Celsius is going to equal 400 minus 273. And over here, it's going to equal, what does that give you? 127, right? 127 Celsius. Okay? Oh, let's try one more with a negative value. Make sure we don't screw that up. Convert Celsius, negative 25 degrees Celsius, to Kelvin. Let's try that. Same equation. But when you plug your numbers in this time, you get a minus 25 plus 273. What do you get? 248, is it? Right? Is that right? 248.
Oh, that's a set.
All right. Now, before you go, copy these 2 down, and the other one was from yesterday. Get all those copied down. I'm not going to check it tomorrow, but